Okay, back to this. So u is equal to cosine x, du is equal to sine x dx, right? Negative sine x dx. And then I make my sign change there, right? So that it matches. So how can I rewrite that first integral right here then? One over u, 1 over u du, right? Negative du. So that becomes negative integral 1 over u du. And then on this one over here, it's going to become what? Plus integral u du. Do you see it? And then those two you can integrate pretty quickly. Antiderivative of 1 over u is natural log u, plus antiderivative of u is 1/2 u squared, plus your constant, and then plug u back in. Okay, I'll do one more. If there's another one, anyone have a question? No? All right, anyone? 17? Well, let me do a new page here. Number 17, tangent secant cubed, that one? So integral tangent x secant cubed x dx. So hopefully in doing the homework you kind of realize that when you've got tangents and secants, it's going to be one of two things. It's going to be u is going to be tangent or u is going to be secant. I mean that's what should happen. If I let u be tangent, then what does my du need to be? Secant x tangent x? Or sorry, secant squared x dx. That's the derivative of tangent, right? Right? Now, I could try this. I'm doing this in red, right? Tangent x, secant x, and then secant squared x dx. And if I did that, then I've got my secant squared dx right there, correct? And I've got my tangent u right here, or tangent x. But the problem is that secant x. Can I get my secant x in terms of tangent? And there's no quick identity to turn secant into tangent. So this looks like it may be leading me down the wrong road. So let me try the other way. All right, the other way would be, and I'll just do it underneath here, is to let my u be equal to secant x. The derivative of that is secant x tangent x dx. And now I can try and rewrite my integral. I'll have to peel one secant off and make it join up with the tangent, right? To be my secant tangent. So that'll leave me a secant squared in the front. And then I'll have my secant that I peeled off, and then the tangent that I just moved to the back. And now I've got my secant x tangent x right here. That's my du. And I've got my u, which is secant x. I've got that right here, u, and it's being squared. So that's just going to be a substitution. And my new integral becomes what? Integral u squared du, which is 1/3 u cubed plus c. And then replace u with secant. Yes. Mm-hmm. Mm-hmm. If the cube was on the what? Okay, yeah, so if we switch it and put the cube on the tangent and take the cube away on the secant, like that one, right? Okay, so what would happen here? what happened here. So do what? So peel one of the tangents off, so you have tangent squared x, tangent x, secant x, that thing? Okay, so if you peel off one tangent, then can you kind of see that you've got a secant x, tangent x, dx like this? That's the derivative of secant. But you don't have secant, you have tangent squared, but there's a Pythagorean identity that allows you to turn tangent squared into secant squared x minus 1, secant x, tangent x, dx. Then distribute. So you basically have two integrals. The first one is secant, watch the way I do this, secant squared x, secant x, tangent x, dx, minus new integral, secant x, tangent x, dx. You don't have to do it this way, but maybe this will help make sense. You see what I did though? I took this whole thing, distributed through to both. Now I left my secant squared out here and I didn't turn it into a secant cubed. The reason is that's my u.
That's just like the other problem?
Yeah, it's just like the other one. So that's my u squared du. The other one though, that's the derivative. You should know the antiderivative of that because you know from Cal 1 the derivative of secant and secant tangent. So the integral, the antiderivative of that is just secant x. And then your plus c, and then you got to do what? 1/3 secant cubed x over here, and then minus between them. That make sense?
Yeah.
So it's a lot of playing with these identities, right? Okay. Now, I stopped us at what? 20, where did I stop us? 25 or 27 for homework? 25. I just want you to know I'm going to stop there. If you look at like 29 through 35 or whatever, it goes on and starts doing like integrals with cotangents in there and cosecants. And it works the same way. Just like with tangents and secants, you had the Pythagorean identity, 1 plus tangent squared x equals secant squared x. You have an identity also with cotangents and cosecants. So you can look on your formula sheet. Those work the same. So I'm not going to invest any time. I don't even think I'm going to throw anything like that on the test. So I'm going to stick to secants and tangents and cosines and sines. But just be aware that that's there also. It's just an extension of what we were already doing. Okay? All right. So now we're going to get into the next part of 6.2, and hopefully we'll get into 6.3 today. So 6.2, we are talking about trig substitution. What we did before, okay, what we did last class and what you did for homework was called just trig integrals. You had integrals with trig stuff in it, right? This is different. These are integrals where we're going to make a trigonometric substitution. These are some of my favorite integrals because they require a lot of knowledge of triangles and stuff from pre-cal. So let's start with an example. Let's start with an example here. And I think I want to start with this one right here. Integral x cubed square root x squared plus 4 dx. Now that looks more like something we would have seen on our test, right? Our first test. So any ideas of what you might be tempted to do on something like this? Just like a basic substitution? Like u is what? X squared plus 4? You try the whole thing? Let's just see what we would get. If we go u equals x squared plus 4, then du is 2x dx. We don't have a 2x dx, do we? I could multiply by 1/2. Do I have an x dx? I could rewrite this integral x squared square root x squared plus 4 x dx. So I just peeled 1x off to the back, didn't I? So here's my 1/2 du, right? Is this x dx? That's all this. I've got my u, which is x squared minus 4, right? That's going to go here. And then what about the x squared? Yeah, this x squared, I could actually take this and solve it for x, couldn't I? And replace it with what? Or solve it for x squared. You could replace it with u minus 4, couldn't you? And we would be able to work this integral this way, wouldn't we? Do y'all see that? Okay, but instead, I want to show you a different substitution. It's called Trig Substitution that you can use when you see integrals like this. Now, maybe this is the way you'd want to do this one, and you're happy with it. But there are some integrals you can't do this way that trig substitution is the only thing you can do, all right? So here's the substitution, the trig substitution. Okay, the trig substitution says this. I'm going to put this in red. And just if you're referencing this, this is on page 322 in the book. There's a table in the center of the book that has these 3 different forms. I'm going to do these one at a time. So it says if you have a problem where you have something that looks like this, a squared plus x squared. Okay, so I'm going to put next to this if you have an integral that has square root of a squared plus x squared, where a is a constant, all right? A is a constant. Then you make the substitution x equals a tangent theta. Now there's going to be 3 of these. This is the first type of trig substitution. Yes?
There's something like that
I'm sorry? Yes, there are formulas, but those formulas only work in certain, like it has to look exactly like that, right? So these trig substitutions, this substitution right here, will work if you have that form. It's something we can try, all right? Now, please understand what we're doing is we're making a substitution. We are going to go, and everywhere that we see an x in our problem, we're going to replace it with a tan theta. So we're introducing a new variable, theta. Just let's see where this goes, okay? It's gonna help us quite a bit. All right, now do we have that? Do we have this form? Do we have this? Yes. What's a for us in this problem? All right, this is it right here. So a for us is 2. Right, this right here is our a squared, but that means that a is 2. Follow? Okay, let's make the substitution. I'm going to rewrite the integral down here. Integral x cubed square root 4 plus, no, was it 4 plus x squared? Okay, I'm going to make a substitution right below this. I'm going to write x equals, for us, a tangent theta. So a was 2, so 2 tangent theta. There's my substitution. Now, that means I can replace x with this, right? Now, before you get ahead of yourself, let's check something out. What's dx? What's the derivative of both sides of this equation? So what's the derivative of 2 tangent theta? 2 secant squared theta d theta, right? That's the derivative of both sides of that equation. Follow me? And just for the heck of it, what is the square root of 4 plus x squared going to turn into for us? So that's square root of 4 plus, what is our x right here? What's our x squared? What is this thing right here? 2 tangent theta. What do you get when you square it? 4 tangent squared theta, right? And I can factor a 4 out of that, right? Underneath that root, each term has a 4. So the 4 can come in front like this, 4, 1 plus tangent squared theta. But what is 1 plus tangent squared theta? Secant squared theta, isn't it? So this becomes 4 secant squared theta. And what's the square root of 4? And what's the square root of secant squared theta? Secant theta. You follow that logic? Replacing your x with 2 tangent theta means that we're going to be able to take that big ugly root with all that junk underneath it, right? All that big ugly thing, and we're going to be able to replace it with what? 2 secant theta, right? Is that okay? And then, going back up to my root, I'm going to be able to replace that with 2 secant theta, right? What about my dx? What am I going to replace my dx with? This thing, right? Right there. 2 secant squared theta d theta. The only thing left for me to replace is what? The x cubed. But isn't this x, right? So can't I just cube both sides of that? And it would become what? X cubed is 8 tangent cubed theta, right? All right, I'm going to rewrite the whole integral now. All right, I'm going to go, let's see. It'll become integral. What was x cubed? 8 tangent cubed theta. And then what was the square root of 4 plus x squared? 2 times secant theta times dx, which is 2 secant squared theta d theta, right? Don't forget the d theta in there. Now I'm going to move that up, but I was just trying to give myself some room. You know what? I don't want to erase that. Is that all right? Let me clean that up. On all this, I'm putting it into this integral right here, this thing right here. I'm replacing the x cubed with 8 tan cubed theta, replacing this square root with this, replacing the dx with this. There's 3 different pieces that I figured out, and I'm putting them all back in there now. As it's written at top, yes. Now, what you'll notice is my integral now doesn't have x's anymore, right? What does it have? It has thetas in it. So let me clean this up. What constant can I pull out of this integral? There's 2, 2, and an 8, so, right? So 32 can come out. I have a tangent cubed theta. And I have a secant what? Cubed theta d theta. What would your plan of attack be for this? Peel off a secant and a tangent? Maybe? See, now this is what we did last class, right? We've turned this problem into something from last class. 32 integral, let me try it. Tangent theta, tangent squared theta, secant squared theta, and then I'm going to put the secant x tangent, no, I just switched my variable, oops. Secant theta tangent theta d theta. So what am I thinking I'm going to want for my u here? I'm going to want a secant for my u, right? Because I've kind of peeled off a secant tangent, so I'm thinking maybe I can get everything in terms of secant, right? Yeah, tangent squared is going to be secant squared theta minus 1. And then I'm going to multiply everything out, correct. Does that make sense? I have to keep working through this problem. Maybe in I'll do like another example, and eventually today, once I get it here, I'll say, and now you could do the rest, okay? All right, so 32 integral secant squared theta minus 1, secant squared theta, and then secant theta tangent theta d theta. So I'm not touching the secant theta tangent theta at the end. Distribute through. How many secants do I have here? Secant fourth theta minus secant squared theta, and then here's my secant theta tangent theta d theta. Is this all right? I don't know if the looks I'm getting out there are looks of I'm good with this, or if... All right. I'm going to go ahead and make my substitution. U is equal to secant theta. Du is equal to secant theta tangent theta d theta. And so my new integral becomes 32 integral u to the fourth minus u squared du. Do you agree? What's that? Antiderivative now? So 32 times, let's see, 1/5 u to the fifth minus 1/3 u to the third plus some constant. (32/5), right? 32/5 u to the fifth. But what was u? Secant theta, right? Secant theta to the fifth minus 32 thirds secant cube theta plus c. Still with me? But we're not done, because everything's got to be back in terms of x, right? So there's several ways to get it back to x. Here's the way that I would like for you to maybe learn this or understand it. What you'll do is you'll come back to the very first thing we did, the substitution. What was our substitution? X is equal to 2 tangent theta, right? I'm going to come all the way back down here, and I'm going to write that next to this. X was equal to 2 tangent theta, right? Yes? That means that x over 2 is equal to tangent theta, right? If I divide both sides by 2. Now I'm going to go back to pre-cal, and I'm going to draw what we call a reference triangle. If this is a right triangle, and if I call this angle in here theta, then tangent of that angle is the opposite over the adjacent, isn't it? And since the opposite over the adjacent must equal x over 2, that means I could call this side of it the triangle x and this side 2, couldn't I? So doesn't that triangle represent, this triangle represents this equation that I have down here. The relationship that we have in our problem is represented by that triangle. Now what is it that we want to know here? What's secant theta, right? Secant is the reciprocal of cosine. cosine is adjacent over hypotenuse, right? So we want hypotenuse over adjacent. Can you solve for the hypotenuse of that triangle? Can you tell me what this side of the triangle is, the hypotenuse? Pythagorean theorem will tell us x square root of x squared plus 4, isn't it? A squared plus b squared equals c squared. So c equals the square root of a squared plus b squared. Yes? So secant of theta, according to that triangle, is what? Is what? You can't plug anything in. What's secant of that triangle? Secant of theta. Which side over which side? Hypotenuse over adjacent. So that's the square root of x squared plus 4 over 2. So I'm ready for my final answer. This equals 32 over 5 secant theta, which is the square root of x squared plus 4 all over 2, all raised to the 5th, minus 32 thirds secant theta, which is square root of x squared plus 4 all over 2, all raised to the 3rd, plus c. And that, my friends, is your first example of trigonometric substitution. Yeah. Sometimes when you get real excited, you get sick. I know the feeling. Now, my approach to this problem would have been the first way I showed us, right? When we started, and I said, oh, we can do it that way, but this will work too. So this wouldn't be the way I would approach this. But there's problems where we can't approach it any other way but this way. So let's do another one, okay? Integral one over x square root 5 minus x squared dx. So we could mess with some, hey, let's try this for u and du and try our basic stuff. But because today's about trigonometric substitutions, let's see what we can do if you have a square root of an a squared minus x squared. The previous problem, it was a squared plus x squared, wasn't it? What do we do when we have a square root of an a squared minus x squared instead? So again, referring to page 322, we make the substitution of x equals a sine theta. A sine theta. So that's what we make our substitution to be. Question that I have to start with for you is, what's a? It's the square root of 5, right? Because 5 up there, the 5 here is a squared. So a has to be the square root of that, which is the square root of 5. So be careful with that. So here's our substitution that we're going to make. I'm going to make the substitution a equals, or not a equals, sorry, x equals, what? Root 5 sine theta. Okay, that's what trigonometric substitution tells me to do. If I see a square root of a number minus the variable squared, I make that substitution and things should become nice. We'll see. Should. So what did I do last time? I did that and then didn't I take the derivative of it? So take derivative of it. That way we can get dx. What would dx be? Root 5 is a constant. Cosine theta d theta. So that's just derivative of left and right side. Then didn't I take that whole square root thing? 5 minus x squared. And didn't I figure out what that would be? What's this going to be for us? Square root of 5 minus, what's x squared for us? Square the x. Root 5 squared, which is 5 sine squared theta, right? What can you factor out of both of those? A 5. So I have root 5 and then 1 minus cosine squared theta. Oh, shit, sorry. I'm getting ahead of myself here. 1 minus sine squared theta, right? That's what happens when I factor a 5 out. And 1 minus sine squared theta turns into 1 minus sine squared theta turns into cosine squared theta. And if I take the square root of that, I get square root of 5 cosine theta, don't I? I can take the square root of cosine squared, it just becomes cosine. The square root of 5 I can't do anything with, so it's still root 5. Now, go ahead. Yes?
I get confused when you want x dx. How come you don't mess with the square root of 5?
Because it's a constant.
Okay.
So it's like, what's the derivative of like 3 sine theta? The 3 is just there, right? What's derivative of sine? Cosine, then you bring the 3 in.
Okay.
Sure? Okay. I think I'm ready to rewrite the integral. Y'all ready? What am I going to replace? Well, let's see. Do I have everything? Do I have something for x right here? Do I have that x bottom left corner there? I do, right? Root 5 sine theta, right? Do I have something for that square root 5 minus x squared? That's going to come down here. That's my square root of 5 cosine theta. I think I need more highlighters, don't you? Let me see here. I'm letting you work real quick. Oh, no. That'll work. Okay, so what else do I need to replace? I'm forgetting something here. What do I still need? The dx, right? The dx, let's see how this turns out. And what's dx going to be for me?
Square root of 5 is cosine.
Yep, cosine theta d theta. So now I've got everything in terms of theta. I'll write it up here since I've got it. I'll just write it right here. It's integral 1 over x, which is root 5 sine theta. Then I have that square root of all that junk, which turns into another root 5, this time cosine theta. And then the dx turns into root 5, what, cosine theta d theta? Sorry, I'm trying to squeeze it in over there. But do you all see where that all comes from? I'll clean it up on the next line. I get some nice cancellation, don't I? I get a root 5 to go away. I get a cosine theta to go away. And that root 5 I can pull out of the integral as a 1 over root 5 integral. What's still there? 1 over sine theta, right? 1 over sine theta, which is cosecant theta. Good, thank you. D theta, isn't it? So that cleaned up rather nicely, didn't it? And we have a formula for the antiderivative of cosecant on our formula sheet. I'm going to continue this down here. I'm at 1 over root 5 integral cosecant theta d theta, which is 1 over root 5 what? Natural log? Cosecant theta minus cotangent theta plus our constant. Did everyone see that? That's off of formula. What number is that? What formula was that? 15? Okay, I'll just put it there. Yes. That's the formula for the antiderivative of cosecant. Look on your formula sheets. Formula number 15. Page 6, number 15. Now we got to get everything back in terms of x. So this is where your reference triangle is going to come into play. I'm going to take the equation I had, my original substitution, x equals root 5 sine theta. I'm going to throw that down here. X equals root 5 sine theta. I'm going to divide both sides of this by root 5. That's sine theta. I'm going to draw a reference triangle. See if it'll allow me to draw a right triangle. Nope, it doesn't. Okay. My right triangle looks pretty bad. So theta is always going to be the angle here. And now it's just a matter of getting everything set up correctly. Sine theta is what side over what side? Opposite over hypotenuse. That means the opposite side should be x, and the hypotenuse should be root 5. And I want both cosecant and cotangent, right? Cosecant is the reciprocal of sine, which I could answer right now, couldn't I? Cosecant theta would be what? Root 5 over x? But cotangent requires me to have the other two sides of the triangle. So you have to solve for this side. If you do, you get square root 5 minus x squared. You recognize that? Square root 5 minus x squared? Wasn't that the thing from earlier? It always turns out that that's going to pop up again on your triangle, but I always think it's more constructive to actually draw the triangle. It means you understand how all those things are connected. All right, I'm ready. Let's do it. So our answer is equals 1 over root 5. Natural log cosecant theta is what? Root 5 over x minus cotangent, which is the reciprocal of tangent, which is adjacent over hypotenuse. Root 5 minus x squared over x. Bam, plus c. Those two fractions have the same denominator, don't they? So I could put them together if I wanted to. Man, I'm concerned about my battery life here. We'll see how this goes. What's that? You think so? Yes. That what? What did I say? Did I say hypotenuse? I wrote down the right thing. I may have said the wrong thing. It's adjacent over opposite. Yeah, thank you. I'm sorry. You see, thank you for correcting me, but this is the right thing written. I may have said the wrong thing. Thank you. Okay, what do y'all think? Now, just for grins, go back up and look at the original problem. Is there a formula on your formula sheet right now that can deal with this integral? Who's got their formula sheets? Can I look at yours real quick? Let's see. There's a lot of formulas on here, and sometimes they fit right into the pattern here. Which one? 18. 18's backwards. 18 has u squared minus a squared, and u is the variable. Close, though.
16 maybe, but there's no x.
16, there's no x out there. 19, it's not, no. 17. Yeah, so it's not exactly there. But just keep in mind that those formulas are there. Guess how all those formulas, how you can get all those formulas? Doing these substitutions. That's how they got them, okay? All right, we need to do some more. Now, there's a certain type of problem I want to make sure that we see. Let me grab it here. $44. Wow, that's a beast. There we go. Okay. This is something like it. All right, let's do this one. I just want to make sure you see this one first. Integral of 1 over x squared plus 1 squared dx. Now this problem doesn't have a square root in it, which is usually what tips you off to use the trig substitution. Notice every problem we've had, it's had the square root and then it's been like a squared plus x squared, or we had a squared minus x squared. So you could try and play a bunch of different games, trying substitutions and do all these different things for this one. You're probably going to run around in circles for quite some time. But you've got an x squared plus a squared, don't you? You have an x squared plus a squared? It's just not under a root yet. What power would that have to be to? The fourth, right? Taking the square root of something and raising it to the fourth power is the same as squaring it. Agreed? Now you have a square root. And I already told you how to handle something if you had an x squared plus a squared, didn't I? I did a squared plus x squared, but it's the same thing, isn't it? So what's the substitution I'm supposed to make here? X is a tan theta. That's my substitution. Now what is a for us? 1, right? So my substitution is x equals tan theta. What do I do now? dx. dx is just secant squared theta, d theta. And then let me figure out what the square root of all that junk is. What does it turn out to be? It's just secant theta. So can I spare us the step where I replace the x with that and square it? Or I guess I've come this far. I'll just write it down. X squared is what? Tangent squared? Theta plus 1. And what is tangent squared theta plus 1? Secant squared theta. So that just turns out to be the square root of secant squared theta, which is secant theta. Is that all right? Can I rewrite the integral now? I'll bring it down right here. What's this integral going to become? Integral 1 over what? What's the square root of x squared plus 1? What is it? Secant theta, but to what power? Fourth power. And then what's dx? Secant squared theta d theta. So I've rewritten the integral. Questions? What does that turn into? 1 over secant squared theta. But what is secant theta? Isn't it 1 over cosine? So isn't that just cosine squared theta? 1 over secant squared. What's up? And then I did this right here. I canceled 2 of them out right there. You're okay?
Yeah.
Okay.
Then it's just cosine square theta?
Yeah, this is just going to be equal to cosine squared theta d theta. And that, you could turn it into 1 minus sine squared. That's not going to help you though.
What is it? Half angle? The one plus?
Yeah, the power reduced one. This is the one where you can take the power down, but the angle doubles. So this becomes integral 1/2 plus or minus on cosine. It's plus. For cosine, when you're trying to power reduce cosine, it's a plus. The way I remember it is when you power reduce sine, it's subtract. Sine, subtract. Cosine is not that way. Yeah, exactly. You can't do it for cosine, but if you remember it for sine, then cosine can only be one other thing, right? Cosine to what? Theta, right? Keep our variable correct here. And that, what's nice about that integral is those two pieces are easy to integrate, right? What's the antiderivative of 1/2? Be careful. 1/2 theta. Good. 1/2 theta, because our variable is theta. Then what? Plus 1/4 sine 2 theta plus a constant. So what did I do there? What did I do? That's just that rule, right? With cosine AX or whatever. Yep, that's old. We happy with that?
So 1 plus 1.
Where did the 1/2 what? The antiderivative of 1/2 is 1/2 theta, because theta is like the x. All right, now we've run into a little bit of an issue here. All right, we have an issue. I need to know what theta is, right? What's theta? See, in the problems before, I wanted to know, like, go back to the previous problem. At the very end of the problem, what is it that I wanted to know? I wanted to know what cosecant theta was, right? Go back, look up here. I want to know what cosecant theta was and what cotangent theta was, so I drew a reference triangle, right? But now I actually want to know what theta is, not cos something of it.
Can you do like 1 over r cosine?
Well, let's go back and look at our relationship again. I'm still going to grab our substitution. This was our substitution, right? X is tan theta. That was our substitution. I'm still going to write that down over here. X equals tan theta. Can you solve that for theta? Yes, how? Take what? I didn't quite hear you. I think you said it, but did you say arctan? Oh. Arctan x. If you take the inverse tangent on both sides of that equation, it will wipe out the tangent on the right, won't it? So what I'm doing is I'm taking the arctangent of x on the left and the arctangent of the tangent of theta, and that gives us arctangent x equals theta. Now there's some domain restrictions on inverse trig functions that we're not going to get into. I mean, it's just We want to get the basic idea here down. That gives us theta, right? Now, we also need to know what in the problem. So we got theta, we're good, we're happy with that. But we also need to know what sine 2 theta is. Now, this is where I might want a reference triangle, right? But it's 2 theta in that trig function. It's not sine theta, it's sine 2 theta. So the only way we're going to be able to recover this is to use the identity for the double angle for sine and turn that into 2 sine theta cosine theta. Isn't that what sine 2 theta is? From pre-cal, it's one of our identities. Sine 2 theta is 2 sine theta cosine theta. What's that? The 1/4 is going to hit the 2, yeah. So let me draw a reference triangle over here on the side. Here's theta. What do I know about tangent theta? Look at tangent theta is what I'm given, right? Tangent theta is x, right? So that means that this side should be x and the adjacent side should be what? 1. Do you agree this triangle says that tangent theta is x?
Yes.
Tangent theta is x. And that means the only thing that this side could be is square root x squared plus 1, right? Do you know what sine is now? Opposite over hypotenuse. What's cosine? 1 over the hypotenuse, right? So I'm in business now, okay? I'm going to roll this answer out. Equals 1/2 theta, which we said is arctangent of what? X, plus 1/2. 1/2 comes from the 1/4 times 2. Sine theta, which is x over root x squared plus 1, times cosine theta, which is 1 over root x squared plus 1 plus c. And you could put these two, or all these together right here, and get something like 1/2 arctangent x plus x over 2 times x squared plus 1, something like that, plus c. Because those two roots multiply together and the roots go away, right? There we go. So the reason why I wanted to show you this problem was because in this one you actually at some point had to solve for theta, didn't you? So you had to come in with that inverse trig function. That's why I wanted you to see it. All right, what time is it? 2 o'clock? All right, there's one more type of trig substitution that I haven't done yet. And so I think it's worth at least setting up one problem like this. What have we done? Just to recap. We've done problems where we have like a squared plus x squared. And we've done a squared minus x squared, right? The only other possibility is x squared minus a squared, right? And so I'll just recap this. If it was this first one, we made the substitution x is equal to a tangent theta, right? That's what we did. If it was this one, we made the substitution x equals a, remember? Sine theta, right? And on this one, which I haven't shown you an example of, it's going to be cosine. So remember, what page did I tell you? 322, right? They have them in different order than I presented them to you. This one you would think is the cosine. It's secant, a secant theta. Okay, so a secant theta. Now, what are you going to do on the test if all you have is your cheat sheet? I mean, all you have are your formulas. How are you going to remember these? I don't know. Write them on your hand. Program them into your calculator. He'll never know what you're doing. Okay, you ready? Let's do one more problem. No, I was thinking out loud for a few of you, that's all. I'll never forget this class I took. Wait, what have we not done? Okay, this is a good one. Gosh, what was this class? What was that class called? I took a class. It was called Abstract Algebra, which is probably like a junior level math course. You take it after you take the calculus sequence and stuff. And I was sitting there during I think it was the final exam, and we were in this big auditorium, and it was, I was taking the test, and this guy was sitting like 4 rows in front of me, and he was sitting there taking the test, and on the floor, he had like 8 textbooks opened up. He had everything like laid out completely, and he would actually like crouch down and crawl around on the floor and flip through the book and come back up, and I just sat there and I watched him. I was like, unbelievable, man. And our professor was like, just out of it. I mean, this guy's an old guy anyway, so he's just down there at his desk, and I mean, seriously, the auditorium was huge. You could sit like 300 people in there, and there was probably like 20 people taking the test. So, anyways, after class, I did the test. I turned it in. Afterward, I waited outside, and I waited for that guy to come out, and I was like, sorry, I've never met you or anything, but what's your major? And he's like, math. And I was like, wow, I was like blown away. And I said, well, it shouldn't be math anymore, or something like that. And I told him that if I ever saw him in another class, that I would report him for academic integrity. Because I don't think that's fair, right? In a class where you have to really study your ass off, to have someone else sitting there all, he had basically had Google and Wolfram Alpha right there sitting in his lap, So, cheating, I guess, it'll get you so far, but eventually the reality of what you don't know sets in. Okay, what about this one? Do not mix up a squared minus x squared with x squared minus a squared. I never saw that guy again. And only 7 of us finished that program together. Yeah, so he was done. Okay. This is x squared minus a squared. What's the substitution for x squared minus a squared? X squared minus a squared. We make the substitution x equals a secant theta. So I'm going to come in here and I replace x with a. What's a for us? 3 secant theta. Is everyone at least getting that part of it? Like just transforming, understanding, seeing the substitution. Okay, dx is 3 secant theta tangent theta d theta, right? D secant theta, tangent theta, d theta. And then what about this square root of all this stuff? That's the square root of, what's x squared? 9 secant squared theta minus 9. What can you factor out there? 9, so you get square root 9 secant squared theta minus 1. What is secant squared theta minus 1? Tangent squared theta. And what's square root of 9 tangent squared theta? 3 tangent theta. So all that equals 3 tangent theta. I think I'm ready to rewrite the integral. Y'all ready? Are you going to be able to tell me what this part is? X squared, the square root x squared minus 9? What's that? 3 tangent theta. How about this dx? What's dx? 3 secant theta, tangent theta, d theta. But what about the x cubed?
27 secant cube.
Yeah, you got to cube this x right there. So 3 cubed is 27. Secant cubed is secant cube theta. So it becomes, try and leave that integral up there. Integral, that square root stuff was 3 tan theta. 3 tan theta over the denominator was x cubed, so that's 27 secant cubed theta, and then dx was 3 secant theta tangent theta d theta. You get some canceling, right? Not much, though. I think we get a 1/3 to come out, right? Because we get a 9 on top and a 27 on the bottom, like constant-wise. Then we get a tangent squared theta, and on the bottom, what do we get? Secant, what? Squared theta? Did I lose you? I'm just canceling stuff here. Like one of these secants cancels with one of these, they'll get 2 of them. This tangent and this tangent come together to get me tangent squared. 3 times 3 is 9. 9 divided by 27, that's 1/3. So I'm just cleaning up, right? And now you have a new integral. And at this point, I'm going to say dot, dot, dot. You've got tangents and secants in there. You figure it out. And then at the end, switch back, right? Switch back from theta back to x. Okay, what you should look at for homework is 43, this is page 326, 43 through 59. Let me see, it actually goes up to like, well, that's good. I would say odds here. And I'd say if you want to turn in a bonus for next class, do number 54 for bonus. In 54, it's an integral, and they give you A's and B's. Like they don't give you numbers like 2s and 9s. It's a bunch of letters, so it's a bonus problem. All right, how's my battery life here? That finishes 6-2, and we're going to start 6-3 now. Y'all all right? Want to stretch? Yes.
Problem? Then what would you do after that? Once you have tangent squared over.
I don't know. What would you do after that? That's what you're going to have to figure out. What would I do? I don't know. I mean, I haven't thought about it yet. I would probably do tangent squared as secant squared x minus 1 and split it into 2 fractions. Because you'd have secant squared over secant squared. Over. Wait a minute. Yeah. You get cosine squared, and then you could power reduce that one to get the 1/2 plus the 1/2. Yeah. Yeah. But the way you're talking is the way that you want to start to feel in this class, where like before you even do it, you're actually seeing it all already. You're like, okay. All right, 6.3. Why? You don't like this section? This what? Okay, let me begin this topic with a little asterisk that says that at some point, hopefully in your life, you have seen partial fraction decomposition. It's a way of simplifying a rational expression. So let's start with this expression: 2 over x minus 1 plus 3 over 2x plus 5. And let's go ahead and do an integral on this, okay? Let's do this integral. Let's look at that integral right now. Hopefully you realize that these integrals are pretty basic. But we haven't done a whole lot with these yet, so let's just go through it. I can break this into two integrals, can I? So my first integral, I can factor a 2 out. I can put 1 over x minus 1 dx. The second integral, I can factor a 3 out, and I can say 1 over 2x plus 5 dx. Agreed? Let's break that into two integrals. Now, for this first integral, I'm just going to do a quick little u substitution. U is x minus 1. What's du? dx, right? So that little integral becomes a integral 1 over u du, doesn't it? This first integral is a 1 over u du. And so the antiderivative of 1 over u is what? Natural log, right? So this whole thing on the left side should just turn out to be, what, 2 natural log of x minus 1, right? That's what that integral becomes. Now the other one, when I do the substitution over here, u is equal to 2x plus 5. Du is what? 2 dx. So I'm off by 2, right? I'm off. So I'm going to have to do 1/2 on each side. So it'll be 1/2 du equals dx. And then I can pull that 1/2 out of the integral, can't I? And I'll have 3/2, and it'll still be 1 over u du then. So that becomes plus 3/2 natural log of what? 2x plus 5 plus a constant. This isn't partial fractions yet, okay? I'm just trying to get us to appreciate really this now, okay? Can I go to a new page? I want us to appreciate the fact that if we have any integral that has something like this in it, that means that's a linear expression in the denominator, right? A linear expression by itself. The antiderivative of that will always be natural log of that linear expression, but there's something else. What do I need out front? I need to account for that a in front of the x, just like we did with the cosine and the sine. What did we always come with when we integrated cosine? We had 1 over a, right? 1 over a. Same thing here, 1 over a. So anytime we have a number like a constant over this linear thing, it'll always integrate very easily back up to natural log of 1 over a natural log of it, yes. No, I don't think so. I'm not sure if it is. I don't think it is. Okay, let's keep that in mind. So if we can make things look like that, we should have an easy time integrating those, shouldn't we? All right. Then let's do this. Let's take the integral of x plus 5 over x squared plus x minus 2. Now, do you see something in its derivative? Let's go back to the most simple, primitive way of integrating. Do you see something in its derivative? U is the denominator. What's the derivative of that? 2x plus 1 dx. Do you have 2x plus 1? You don't, right? You have an x plus 5, but you don't have a 2x plus 1. Now, there is a way we can kind of take a bat to this and make it happen, but I want to show you partial fractions. That's what today's about. So let's kind of just sit here and go, okay, that's not really going to go anywhere. So do you agree with this? This integral can be rewritten x plus 5 over x plus 2 x minus 1. So what did I do there? I forgot a dx on that first integral. First time I wrote it down. Forgot dx there. Okay, so I've taken this original integral right here and I've just rewritten it. I just factored the denominator. That's all I did, right? So at this point, I'm going to stop the problem and I'm going to take the expression the integrand, sorry. And partial fractions says that what we can do is we should be able to break this up into two fractions being added together. How many of you have seen partial fractions? We should probably take a vote here. Okay, and it's been a while probably.
Did you drop the integral?
That's why I put the blue line. I'm stopping for a second. I'm going to come back to the integral in a minute. So the way partial fractions works is it says, look, if you look at this left side, if you look at this rational expression, if you have two factors in the denominator that are linear, right? These are both linear factors. X plus 2 is a linear factor. X minus 1 is a linear factor. Then we should be able to break that up into two fractions being added together, okay? Being added together, where the x plus 2 is the denominator here and the x minus 1 is the denominator here. The question is, what goes on top? Okay, and it turns out they will be numbers, but we have to figure out what they are. So what we want to do is not put question marks there. We want to put A and B, capital A, capital B. All right, so here's what I'm going to do. I'm going to take both, this is an equation, right? I'm going to take both sides of the equation and I'm going to multiply it by the LCD. What's the LCD? What's the least common denominator of that equation? The x plus 2 times x minus 1, right? So I'm basically going to take x plus 2 times x minus 1 and I'm going to multiply it here and here. And because I'm out of room, we do it on the other side too, right? We do it on this side, that LCD. What happens on the left side? What happens? What are you left with? X plus 5. What do you get on the right-hand side? That first distribution, when you go and you take that LCD and you multiply times that first one, what cancels? The x plus 2. What's left? Ax minus 1. When you distribute that LCD to the second term, what cancels? X minus 1. What's left? So plus b, and then the x plus 2 is still there, right? So I started off by saying, hey, look, the left side equals the right. Found the LCD, multiply both sides by the LCD. Now I'm here. All right? Now there are two ways to do this, two ways that are normally taught to do this at this point. There's a short way and there's a long way. The short way, if it works, is beautiful. The long way works all the time. So sometimes the short way doesn't work, and you'll know in next class when we run into some problems where you can't use the short way. But this one, the long way is going to work. I mean, the short way is going to work. What am I trying to figure out in this problem? What's the whole thing is all about trying to figure what out? Not x. What are we trying to find? A and B, right? Because if we can take this original integral right here, if I can take that integral right there, and I can somehow take it and rewrite it like this, and then somehow break this down to be two things like that, separated by addition, and each one of those is linear, I can do natural logs on those, right? And it'll be easy for me. It's just figuring out what A and B are. That's all. That's our goal, to find A and B. Understand? Okay, so if I want to know what A and B are here, here's what I can do. I can get a little God complex going on here. I can say let x be equal to -2. Let it be. Why would I let x be -2? Because if I do that, I'm going to kill off the second term over there, right? And it'll become a 0, and that'll kill off the b, but it won't kill off the a term. And so I'll get an equation that just has a in it and a number. So let's do it. Let x be -2. What does the left side of this equation become? This is the equation I'm working with right here. What does the left side become? 3 equals a times -3. And then divide both sides by -3. A is -1. Damn, I already know what a is. Make sense? Now, let's figure out what b is. So you can get your God complex again. Let x be. I guess when I talk like that, I'm implying God is masculine. Doesn't have to be that way. Let x be what? Look, this is one of the few times in math where I have control to do what I want, right? 17. Let x be 1, right? Because I want to kill off the a. If x is 1, it will kill it off. So what does my equation become? 6 equals b times 3. So b is 2. So now I know what a and b are. So now what I can do is I can jump back to the original problem, right? And the original problem, I had factored it, right? It was x plus 5 over the x plus 2, right? X minus 1 dx. And what I'm saying is I can now break that into two fractions. And you have to get these right. What was a? A was -1, and the a goes on top of which linear factor? X plus 2. Don't mix them up. A is on top of the x plus 2. So you've got a -1 over x plus 2, and then plus your b, which turned out to be 2 over x minus 1. And can you integrate both of those? There's two separate ones, right? So you do each one. The -1 I'm going to pull out. Natural log of what? X plus 2 plus, I pull the 2 out, natural log of x minus 1 plus c. Is everyone okay with me going from this to this without any work? I'm just basically using the formula. Going backwards? Ten minutes? One more, we'll call it a day. All right. So check this one out. We're going to spend all class next time talking about probably partial fractions. And that'll be it. We'll be done with techniques of integration. Okay? After that. So then we can get into the business of applying it to something. So this one, I mean, you could sit here and try all sorts of different things. Again, you could try a substitution. I mean, I don't think you would do integration by parts. I don't see a trig substitution here. Like a plus x squared, a minus x squared minus a squared, right? You don't see any of that, no square roots. There's a lot of things that you should start like ruling out. Partial fractions even you should probably rule out because you don't have a denominator that you can break up, right? But there is something you can do with this that maybe you forgot you could do to things like this. Long division. You can do synthetic if it's linear in the denominator, but it's not always going to be linear in the denominator, so you need to know long division. Now, I'm going to do long division on this. Long division is like old school division, right? But with polynomials instead of numbers. I notice I left some space, right? Where did I leave that space? For my nothing x squared. Oh, I left way too much space, actually. For my nothing x squared, right? And that's so I can line everything up. So the way you do long division, in case you've forgotten, is you start off with this first term, x, and you ask yourself, what do I multiply x by to get x cubed? What do you multiply by? X squared. So I'm going to line that up right here under on the x squared column. And now what you do is you multiply x squared times x and x squared times negative 1, and you put those underneath. X squared times x is x cubed. X squared times negative 1 is negative x squared. Now what are you supposed to do? Subtract that row. So I come through and I subtract. So I say, okay, take that row and I subtract it. So I subtract that x cubed. I subtract a negative, which makes it positive. And now let's add down. What do you get? X squared plus x. And now you play the same game. What do I multiply x by, right? What do I multiply x by to get x squared? X. So I put that here, plus x. And then multiply it through. I'll do this one in green, I guess. X times x is x squared. X times negative 1 is negative x. But then you're supposed to come through and subtract. So it makes it negative x squared and makes it plus x. And then add down. What do you get? Just 2x. And then you play the game one last time. What do I multiply x by to get 2x? A 2. So I put plus 2 up there. And it goes in and you multiply through, and what would you get? 2x minus 2. Subtract this, which turns it into minus and then plus. And so what are you left with as a remainder here? 2, right? Now, if you know, you're going to have to Google long division if it's been too long for you. So this is what we get. We get that x cubed plus x over x minus 1 is equal to, what is it equal to? X squared plus x plus 2 plus our remainder 2 over what we divided by x minus 1, right? Remainder over divisor. So check it out. This is actually pretty cool. This integral is this integral. And it just got way cleaner, didn't it? I mean, think about integrating that. I need to throw a dx on the end of that. What's the antiderivative of this? You can go term by term, right? What's antiderivative of x squared? 1/3 x cubed. Antiderivative of x? 1/2 x squared. Antiderivative of 2? 2x plus 2 natural log x minus 1 plus c
The first one should be 1/3 x
cubed. It's right there. I don't know what you're talking about.
It's a program.
Okay, I don't really think we're really prepared to get any homework problems out of 6.3 yet. We'll have to get pretty deep into it next time. But I will say this. When it comes to the partial fractions, all right, when it comes to problems like these, just like any integral here that I've given you this semester, I could beat you to death with integrals. Like I could make you bleed with integration. That's not my goal here. Because like I was talking to a couple of students about this a while back. At the end of the day, in the real world situation, if you have an integral, most likely you're going to go to a computer to integrate it. All right, so this is just, these are the techniques. We need to make sure that we know how to do them. You don't want to be in engineering, you don't want to be in an engineering class and say, yeah, I passed Cal 2, and they throw an integral like this at you. And you're like, Wolfram Alpha, right? You need to be somewhat have some skill in integration. You can't be turning to a computer for basic stuff. And that's what I want you to at least feel comfortable with is, you know, am I making sense? Okay. So we're going to get through these partial fractions. Some of the problems would require solving like systems of linear equations that are like 6 or 7 equations with 6 or 7 variables. We're not going to do that. We'd always turn to a computer for that. So finish up the homework for 6.2 and come in prepared on Wednesday for 6.3 to get your hands dirty. Y'all have a good day.